Okay. Good afternoon, everyone. I think I am the last presenter of this entire conference, so I'd like to have a little bit of patience so that we can finish it. My name is K.I. Iqbal. I'm a PhD candidate at Department of Civil Engineering, and I'm going to talk about identifying lead versus non-lead water service line using non-destructive stress wave propagation and deep learning. So let's get started. Okay. So this is a typical layout of water service line. This is the water main from where water flows through this service line and reaches to the surface, reaches to the house. Now, this part of the service line is known as the utility or public service line, and this part of the service line is known as the customer side service line. Now, these service lines could be made of galvanized steel, copper, PVC, or lead. Now, if one of these is made of lead, then it has a serious health concern for our young people and also for the adult. So, government is trying to replace all the lead-based service line throughout the United States. As per American Water Association, there is nearly 6.1 to 10.2 million pipelines are made of lead-based, and they are installed between 1800 to 1940. As a result, they do not have proper historical records where they installed them, made it a bit challenging for them to replace all the lead-based service line. Now, last August, we have been invited by UK to test in their water research facilities. They also mentioned that this problem is not only in the US, it's also in UK and also part of the Europe. So several groups came forward to help water utilities. They tried to use, some group tried to use historical records, but it's not available to the entire service area. Some group tried to use water quality sampling, but that doesn't tell the source of the contamination. Some group tried to use magnetic test, but magnet doesn't stick to lead, copper, or plastic pipe. Some other group tried to use CCTV, but inserting the CCTV is a bit challenging in some locations. And the last option anyone can think about is to excavate and to see where the material is. And you can see this is actually, we have visited Washington, D.C. In a location. They are testing the types of the materials. So what they had to do, they had to close the entire neighborhood. And you can see the physical disturbance it's causing. So as per American Water Association, they are saying currently they do not have any convenient technology that can actually easily and cost-effectively help them to identify, or at least can tell, is it made of lead or not lead. So we proposed a technology that is based on stress wave propagation. It's a non-destructive testing. It doesn't require excavation. It doesn't require entrance to the house, and also it can tell both the public side and also customer side service line type. So I'm going to show you how this technology is going to work. So again, this is the typical layout of the water service line, and you can see this is the curved bulb. So what we will use a shut-off rod that is basically used by the water utilities to control the flow from the water main to the house. We'll use that rod, and we'll excite stress wave through an instrumented hammer. When we'll hit it, the energy will travel through this rod to the service line, and part of the energy will leak to the surrounding soil, and we can capture those energy using some pre-installed sensors. And by calculating the time of arrival between these two sensors, we can calculate the speed of the wave propagation in the service line, and using that speed feature, we can differentiate different materials. That is our goal. So this is an example of field testing that we did. This is my supervisor who is exciting through the stress wave impact hammer, the stress wave propagation, and through aluminum extension rod. These are two sensors that we use in the field, and this is me collecting the data. We also can set this data acquisition system inside the car trunk, so it's a portable We also can do the test during a slight rainy condition. This is a very recent test that we did in Wrightsville, PA. My colleague, sorry, okay. Sorry, so we'll have to skip it for now. Just to show that how the technology was working in the real condition. Okay. So we considered two hypotheses. One is like to use the speed feature. As I mentioned, speed feature varies for steel, copper, lead, and PVC widely. For specifically lead, it's the lowest. So we can use that feature to differentiate different materials of the service line. The other hypothesis we are considering is like when we generate the stress wave, it also generates both transient wave and steady state wave. That steady state wave causes the service line to vibrate, and those sensors can capture also vibration. So using the vibration analysis, we can actually differentiate different materials, and also we can feed this vibration feature into deep learning model that can also help us to identify service line materials. So for these purposes, we have divided our task into several phases, like we did literature review and understood our theoretical background of a stress wave propagation. Then we did a control lab experiment, and then we did field testing and tried to validate our hypothesis one. Finally, we prepare our data for feeding into deep learning model. So I'd like to go very quickly about the control lab experiment that we did. As you can see, we developed a prototype in the lab where we put our different service line, and then we generated the stress wave through this impact hammer, and we recorded those signals, and you can see we put 3 sensors. They were 35 centimeter apart. And these are typical signals look like when we tested, and we calculated the time of arrival difference between corresponding 2 sensors. And using that, we calculated the speed for different service line materials pipe. Now, as you can see, for steel, we got nearly 6,000 meters per second. And for lead, we got the lowest, 1,300 meters per second. So the lab experiment gave us a hope that we can implement this technology in the field condition. Then we moved to the field testing. For field testing, again, we used the same approach that I described already. We recorded 51,000 samples per second. And then for each service line, we recorded 15 to 20 sets of data to ensure repeatability. And these are the locations. We tested nearly 23 cities across the United States and around 419 service line. Part of the service line, we knew the material types, and part of the data, we didn't know what the material type would be. So those we are blind tested. Now, first we did the test our hypothesis one. We calculate the speed as we did for the control lab experiment. But as you can see in the figure, the real world condition is not same as the control lab experiment. So what we got is that for galvanized steel, copper, and lead, in all cases, our speed is nearly 200 meters per second. That is actually close to the shear wave speed in soil. So we got a bit of setback here, but we moved our direction to the alternative approach. We concluded here that the speed feature is not practical for this specific application. Then we moved to explore deep learning algorithm. We collected a lot of data, so we have to find an alternative way. So for that, we used a convolutional neural network. And for that convolutional neural network, we used a frequency response function as the input. At this stage, we do not have sufficient data to develop a multi-class classification problem, so we only focused on lead versus non-lead, only two class. We used frequency response function for the input because frequency response function gives us the vibration analysis, meaning how a structure or a service line vibrate with different input forces. And we can get that, for our cases, our input force is our hammer excitation data, and the output force is like our sensor data that we are collecting. So what we did is like that. Let's say for a location, we have 20 service lines, and we used 80% of that service lines data for training, 10% for validation, and 10% for testing. Among, let's say, 2 service lines from the validation data, let's consider only 1 service line. So for 1 service line, as I mentioned earlier, we recorded 15 to 20 sets, some cases 10 sets. So 10 hammer strike with 3 sensors yield 30 raw signals. And then we did some signal processing before feeding this data into our CNN model. So that signal processing steps include, we did synchronization of data. If you can look at this figure, we recorded the data with the 5 seconds time window, but they are not synchronized. So first we did synchronize all of the data. And then for our hammer data, it has a limitation. It can capture up to 5 voltage. But in some cases, soil depth is high, you have to hit harder, and then it overranges. So we did interpolation to get the whole shape of our hammer data. In that case, we have the input signal. Then we calculated the FFT of our both input signal and also output signal. Now, if you look at this figure, especially on the high frequency range, there is not that much energy on the high frequency ranges when you look at only the FFT data. But if you look at the FRF data that we get after calculating the output signal divided by the input signal, you can see there are some peaks in the high frequency region. Those indicate that the service lines also vibrates in the high frequency. So we use this data after signal processing. We got 30 FRF signals, each with 1,526 data points. And then we did apply min-max normalization to normalize our data between 0 to 1, and we fed that into our 1D-CNN model. Now, these are our data, total 243 service lines. After all the signal processing step, we got nearly 8,925 FRF data. And we combined copper, galvanized, and plastic into not lead group and lead as a lead group. So this is our CNN algorithm. I am not going to the details of this algorithm, just want to mention very quickly. It has 4 convolutional and max pooling stages. And in the output layer, we have 2 fully connected layers, and we used a sigmoid activation function for binary classification problem. And then let's talk about the results that we have obtained. So when we predicted for a service line, we have 30 FRF data. Now, the CNN model didn't predict like all 30 into same classes. In some cases, 25 of them predicted lead, 5 of them predicted not lead. In some cases, it was evenly splitted. So yeah, we have to build our evaluation criteria to predict a class for that particular service line. We looked at the all prediction of that service line, and then we asked, okay, does majority class exist? If yes, choose that class. If not, we looked only the first 2 sensor data, and again ask the same question, does the majority class exist? If yes, we choose that class. If not, that means in that case, we choose the service line as lead, because we are trying to prioritize our lead prediction. Okay. So using this evaluation criteria, we perform the evaluation on our test data, and using this approach, we got 80% accuracy on the test data. And if you look at this confusion matrix, we got 6 out of 7 lead case correct, and 10 out of 13 not lead case correct. After developing this model, we have a bunch of blind testing data. So what we did is like, we predicted those blind tested data service line using our approach, and we gave prediction to the water utilities, and they returned to us with their actual information and said which one we got correct and which one we did wrong. So we gave them a total of 41 predictions, and you can see that out of 7, we got 5 lead case correct, And for not late cases, we got 28 of them correct. So right now, our model's performance 80.48%. And as I mentioned at the beginning that we did some test in Wrightsville, PA very recently that we didn't actually provided the results to them yet. But we got 25 out of 29 correction. And the current accuracy is nearly 83%. So using this approach, we got accuracy on the test data around 80%, and for blind testing data, it was 83%. So these results suggest that the stress wave propagation technology that we proposed with the signal processing and the 1D-CNN model, we can use this technology in the real world to solve our problem, to identify late versus non-late service line. The work is not finished. There's still some other additional work to do. Like we have to develop like a model that is dedicated for public side and private side would be better. That is something we are working on. And also instead of only 1D-CNN, we can explore some other alternative AI architecture. That will be our future work. I'd like to thank my supervisor, Dr. Ivan Bartoli, and also my colleagues for their tremendous help during developing the technology and also during the field testing. Thank you so much for being patient. I think I'm done. If you have any questions, I'll be happy to answer. Thank you. Yes.
Great talk, by the way. Just a question about soil type affecting accuracy of your data, or maybe like threshold of how you're determining what lead is in your vibration test. So I noticed you were doing a lot on the East Coast. Do you think if you were to do your test somewhere else, like with a different soil composition, that you would have different outcomes in your data in terms of accuracy or determining which metal is which underground?
Okay, thank you so much. That's a great question. So I tested in 23 cities. So they, even in Philadelphia, we tested several locations. The soil condition was not same. So yes, that definitely affects, especially the first hypothesis we considered. Because of the soil condition, it was not working. But the vibration testing, I think that's affecting our results. But right now, we are using only 243 service lines data. The AI, it tends to work with more data, right? So if we can collect more data, I think it will be more effective in future. Yes.
You mentioned in your future work developing models for both private and public lines. Why does there need to be a difference?
Let me see if I have some pictures. Let me see. Okay, yep. So these are the actual field conditions. You see the roadside has asphalt, very clean. On the private side or the homeowner side, sometimes we have grass, sometimes we had to deal with concrete, sometimes we had to deal with brick surface. So those actually put a challenging to get a more better accuracy. I think if we can separate our model, definitely our prediction will improve. But the reason we couldn't do that at this time, we had to take permission from the water utilities to get the testing done. And we only tested more lead location on the home side, not on the road side. As a result, we couldn't develop the separate model due to the data limitation. Yes.
One thing, you use only imaginary and real part of the Fourier transform as a features, right, for your
I use both, real part and imaginary part.
Okay. Is it common? I mean, I haven't seen much.
Actually, like you can use the absolute value also, but
Like a power or phase or amplitude or phase separately.
sorry.
So usually, like a Fourier transform gives you two properties, right? Amplitude and phase.
Yes.
And people would understand easily if you say, like, hey, I use the amplitude and phase.
Yeah, you are right. You are right. But
Why do you think like that?
okay, I think you're right. So it's like a it's a complex equation actually, A plus IB, right? So A is the real part, B is the imaginary part. That is what I actually used. And you can get actually the one you're taking or talking about only amplitude, that is the absolute value, plus the phase. We definitely can do that, but we focus on this part to do this way. It's under review. Sorry. Okay. Yeah, yes. Okay. No. That I should keep in remember. Yes, you're right. Thank you so much. Thank you so much for pointing that out. Yes. Any other question? Yes.
What I really appreciate about this is that it is such a smart and cool way of addressing a very pressing need. And I really appreciate that you brought that out first, that this is something that's really necessary. As someone who had lead poisoning, I can attest to that.
Yep.
Permanent brain damage to the wind. And I just wanted to know what kind of interest or feedback did you get from like utility companies and municipal government?
Okay.
So many stakeholders.
Yes, there is I showed at the beginning there are some other groups also trying to solve this problem. Right now there is another company we are competing with. I not say competing company, that is research group, that is say. So far like we have tested nearly 23 cities across like 6 to 7 utilities: Philadelphia, New Jersey, American Water, Pittsburgh, Cincinnati, Water Research Foundation, and also UK. So what they mentioned is like that, so far our technology is convenient and easy to apply, and they do, like we can test in a single day 20 service line. So if you want to excavate, or if you want to, if they want to use the other approach, they also need the access to the home. But for our case, we do not need access to the home, so we can do it, without only if utility says you can do the test, we can do the test. So that's their feedback, but also they are saying maybe focusing how to get more lead prediction correct. That is what they are like focusing. So which actually, I didn't show the results yet. We developed another model, and by combining these two models, we can get actually all the lead prediction. That is something out of this, sorry. Thank you so much. Thank you so much. Okay.